Hello, and welcome to Chapter 2, Section 6. Today we're talking about derivatives of inverse functions. So before we get into this section, I kind of want to recap a little bit about inverse functions. So first of all, remember if you're given an equation you want to find an inverse, you had to switch the x and the y variable and then solve for y again. So that basically, if you were to graph it out, would give you a graph that would reflect your original graph over the line y equals x. Because of that whole like switching the x and the y thing, that's why it's reflective over that. So remember, y equals x is like that diagonal line with a slope of 1 going through the origin. And so if you reflect it over that line, then you're also basically just switching all your x and y coordinates. So if you originally had a point of, I don't know, like 4 comma 1, then your new graph would have, or the inverse graph would have a point coordinate of 1 comma 4. So the x and the y coordinates just switch. So what we want to do with our inverse functions is basically find the derivative at a point. So it's kind of like finding the slope. So derivative at a point is just the slope of the tangent line at that point. So just a reminder, if you see this f with like a kind of like a -1 exponent, this is just talking about the inverse of f. So the original function would be like f of x equals whatever, and then f -1 would be the inverse of f of x. The prime symbol here is just talking about the derivative. So remember, like f prime just means the derivative of f. So here we're finding the derivative of the inverse function at a point. So for example, let's say we're trying to find the derivative of the inverse at x equals 26 for the equation f of x equals x cubed minus 1. So following the formula, we're going to start on the very inside of the parentheses. So we're basically looking for the inverse of where x equals 26. So as we talked about earlier, since inverses are just the same as the original function with the x and the y coordinates switched, then the inverse of 26 would just mean that the original function, instead of 26 being an x value, in the original function, the 26 would be a y value. So f of x, being another name for y, equals 26. So what is the x value at that point? So we were told that f of x equals x cubed minus 1. So we can set 26 as the y value, or f of x, and solve for x using this equation that they gave us. So I'm going to add 1 to both sides and end up with x cubed equals 27. So that means x equals 3. That means for the original function, when x equals 3, y equals 26. So that means in the inverse, there's a point 26 comma 3. So that means the inverse at x equals 26 equals 3. Now that I know that, I can follow along with the rest of the formula now. So if we are trying to find the derivative of the inverse at 26, plugging in my x value of 26, I just found this portion right here. So now I can say I am trying to find now f prime of 3, because we just established that at the inverse when x equals 26 is 3 from here. So at this point, really all we need to do is find the derivative of f and plug in 3, and then that goes on the bottom of this fraction here. So the derivative of f is 3x squared, because our original equation, x cubed minus 1, the x cubed, the derivative would be 3x squared. The minus 1 is a constant, so that would just be 0. And then we're going to plug in x equals 3. So this will give me 1 over 3 times 3 squared, which is 1 over 27. So the derivative of the inverse when x equals 26 is 1 over 27. All right, let's do another example together. So this time f of x equals x squared minus 3x plus 8, and we're looking for the derivative of the inverse when x equals 12. So again, we're going to follow the formula. We're looking for the derivative of the inverse at x equals 12. So first we need to find the stuff on the inside of the parentheses here. the inverse when x equals 12. So this part right here. This means that if the inverse has an x value of 12, that means the original function has a y value of 12. So we're going to set our f of x, which was x squared minus 3x plus 8, equal to 12, and solve for x from here. So because I have an equation with an x squared in it, this makes it quadratic, so we can either solve by using the quadratic formula or factoring. Before I do either of those things, though, I have to set it equal to 0, so I'm going to subtract 12 from both sides to leave me with x squared minus 3x minus 4 equals 0. And this looks like it factors pretty easily into x minus 4 and x plus 1. So that means x equals 4 and negative 1. Okay. If I get two answers for x here, that means I'm going to end up with two answers overall when I look for the derivative of the inverse at x equals 12. Okay, so from here, we are basically following the formula again, f prime of 4, and we also need to find f prime of negative 1, because those were the two numbers that I got for when the inverse at x equals 12. The derivative of f would just be 2x minus 3. And so we're going to plug in x equals 4 and x equals negative 1 to get our two answers. So when I plug in x equals 4, I end up with 1 over 8 minus 3, which is 1 over 5. And if I plug in negative 1, I end up with 1 over negative 5. So those are going to be my two answers, 1 over 5 and negative 1 over 5. And it's not always just going to be one is the negative version of the other. It's just coincidental here. All right, so next I want to talk about derivatives of inverse trig functions. Inverse trig functions are the ones like arcsine, arctan, arccosecant, and so on. Or if you see like sine with the little negative 1 there, those are the inverse ones. Here are all the formulas. Highly recommend you write them down somewhere so that it's easy to refer to. So the way I have these set up is that they're already going to include the chain rule. So normally, if this was just like arcsine of x, so this is like the most basic derivative, then on top here, this would just be 1 over square root of 1 minus x squared. The easiest possible. But because most of the equations you're going to find derivatives of involving inverse trig functions is going to be more complicated than just arcsine of x, I've also included the chain rule version here. Because remember, chain rule means we're going to take the derivative of the outside times the derivative of the inside. So when I say outside and inside, the inside part would be like whatever's in for you, like whatever you're taking the arcsine of. So if that's the inside, then the derivative of the inside we could write as u prime, and it would just get multiplied. So like the bottom part is more of like the derivative of the outside. The numerator is the derivative of the inside being multiplied. But yeah, and that'll be for all of these. All right, let's do an example together. So let's say we're trying to find the derivative of arccosecant of x squared. So first of all, you might not always see parentheses around the x squared, even though it's technically like our inside. So just be aware of that. Be ready for it. So here we're using arccosecant. So we're going to look at the formula for arccosecant, which is this one right here. So our inside, we are saying, is going to be x squared. So if you want to think about that as like u instead now, that's fine. Then following our formula, on top we have negative u prime. So it'll be negative. U prime is the derivative of our inside. So the derivative of x squared is 2x. On the bottom, we have absolute value of u. So u is our inside stuff, which is just the x squared, times the square root of u squared. So u for us was x squared. We're going to square that and then minus 1. So simplifying this out, I have the negative 2x on top. And then I have absolute value of x squared. So if you remember, absolute value is something that always turns things positive. And if you square something, it's also already going to be positive all the time. So really, it's redundant right there. Whether I have the x squared or the absolute value of x squared, it's still going to mean x squared, whatever number you get from that, but the positive version. So I'm not even going to bother putting the absolute value again because squaring x is already going to give me a positive number. So I don't need the absolute value. Again, redundant. On the inside of the square root, I have x squared squared is x to the fourth and then minus 1. So the derivative is going to be negative 2x over x squared times the square root of x fourth minus 1. All right, this next example is slightly more complicated. We are taking the derivative of arc cotangent of e to the x over 3 power. Whew. So here, technically, we have two different things to as u, or because I have stuff inside the parentheses, but then e to the whatever power, that itself also has another derivative. So slightly more complicated here. Okay, so first of all, we're using the arc cotangent derivative, so that's this one right here. Following that formula, our inside, or u, is going to be e to the x over 3 power. So u prime for us is going to be the derivative of e to the x over 3 power. But e to the x over 3 power also requires chain rule because it also itself has its own inside. So if the inside is x over 3, or if you want to think about it as 1/3 x, then the derivative would be e to the stuff, which for us is x over 3, multiplied by the derivative of the inside, which is going to be 1/3 if the inside is 1/3 x. Okay, so that'll be u prime. So when we follow our formula for our cotangent, for the derivative of our cotangent, it'll be negative u prime. So u prime we said was 1/3 e to the x over 3 power divided by 1 plus, and then u for us was e to the x over 3 power, and we're squaring that. So simplifying this out, I'm going to end up with negative 1/3 e to the x over 3 power over 1 plus e to the 2x over 3 power. Because remember, if you have exponents being raised to another power, they would multiply. And there's nothing to simplify here because e to the x over 3 on top and e to the 2x over 3 on the bottom is connected to that plus 1 there, so can't cancel or anything. And that's it for the derivative. So the complexities of this came from having to do chain rule again, but that's it. And that's it for the section. Thanks for watching. It's a short one. Oh, before I say bye, first of all, extra credit for watching till the end. So if you can name the episode that this shirt is from, send me a message on Canvas, and then I'll give you some extra credit. Okay, bye!